Okay, welcome to the February KEGS 2015 meeting. So I will start by introducing our speaker for today, Dr. Peter van Straaten. He is a geologist with a PhD from the University of Göttingen, Germany. He conducted field work for his PhD in Uganda on Precambrian geology along the Western Rift Valley. For almost 10 years, he has worked for United Nations projects as a field geologist and exploration geochemist in East Africa. Actually, Peter has 40 years experience working in all sorts of places in Africa. He seems to like it very much. It's nice and warm there, he tells me. Okay, in 1984, he expanded his career and introduced the new interdisciplinary science of agrogeology, geology in the service of agriculture. So for this, he moved to the University of Guelph, Canada. Supported by Canadian international funding sources, he carried out agrogeological projects in Eastern and Southern Africa, Asia, and South America. At the University of Guelph, he taught undergraduate and graduate courses in structural geology, economic geology, environmental geology, and agrogeology. In 2007, Dr. Van Straaten retired and became Professor Emeritus at the Ontario Agricultural College of the University of Guelph. He has published 3 books, 10 chapters in books, and more than 40 papers. Currently, Dr. Van Straaten is visiting professor at the Federal Rural University in Pernambuco, Brazil, as part of the Brazilian government's program Science Without Borders, and collaborates with soil scientists, agronomists, and geologists in agrogeological projects in southern Brazil, Uganda, and Indonesia. And actually, there's another book or 2 that he is editor of that's coming out of that work in Brazil. And I found out also today he's president of the Ugandan Agrogeology Association. He has built and is currently building a school in Uganda, and especially encouraging lots of local development and initiatives in Uganda's in many of these countries. Now, this is a subject I find very interesting because we usually think about geophysics here at these meetings as instrumentation, case studies, mineral deposits, maybe some oil and gas. But, you know, we have a little bit of a downturn in those subjects, and we really can expand a lot of our geophysics knowledge in agrogeology, as in today's talk. Last month, we were talking about using geophysics to measure sea ice for climate change. People are using them, getting more into geophysics for structural geology, and all sorts of other disciplines that we can use our skills for. So I would like to have you all welcome Dr. Peter van Straaten and his talk, The Role of Geophysics in Agrogeology.
Thank you very much, Edna, and for the introduction. As you have heard, I'm a geologist, mainly a geologist. A geologist by heart, but worked in many fields, from hard rock geology, soft rock geology, exploration geology, and finally in 1984 I turned the corner from looking after gold and nickel to look for something which I thought was more relevant to the majority of the people in Tanzania, where I lived at the time. We looked at geology for agriculture. First of all, I must admit I did not like soils when I was a typical geologist, because soils obliterate our rocks, and we rather like to move them away, say they are overburdened, and so it was a learning curve going into soil science with colleagues, and it was a great pleasure to work with soil scientists. We did not speak the same language though, and it was a long process of mutual learning and getting to understand what soils are, what soil deficiencies are, and where we geologists can contribute something. So after soils, at present I'm working lots with crops, and I will show you this in my presentation. that soils and plants and crops are very important too. So agrogeology, I will introduce this, is quite a multidisciplinary science, and it's relatively new. I thought we had coined the word agrogeology in '84, but going on Google you find out that there were already some people in 1914 or so who were actually soil scientists who used the word agrogeology. And then soil science and geology split. They went their own ways, and I see this now as a reunification of this geological and soil science streams. I will briefly outline what is agrogeology, and then I want to put emphasis on geophysics. What is the role of geophysics in agrogeology? And I must admit, although I'm a geologist, I really like geophysics, the application and interpretation of geophysical data that can help us in many ways in agriculture. So, the relationship between parent material and soils and the role of geophysics is one topic, and the other one is the role of geophysics in discovering agromineral resources. And finally, I will give you a little outlook. So there are two aspects of agrogeology. One is the influence of parent material on soil development and soil fertility. And the other one is the beneficial application of rocks and minerals to enhance the productivity of soils. I call this rocks for crops. In fact, I published 2 books with rather similar names on this subject, and if you're interested, just punch into Google rocks for crops and you can find at least one book online on the agromineral resources of sub-Saharan Africa. The influence of parent material on soil development is quite clear in many cases. When you have a sharp eye, you will see, for instance, here the light gray soils in the background. They are underlain by granites, and in the front here we have dark red-brown soils, and they are underlain by mafic rock types. So iron-rich, I think in this case it's an amphibolite, and you can see these differences sometimes very easy. The geology and soil fertility is quite well illustrated when you look at this satellite image from Zimbabwe. Here you can see the Great Dike. I think it's approximately, on this scale, 600, 700 kilometers long intrusive dike. And then you see on the sides here in red, these are red soils, these are greenstone belts, relatively fertile soils. And then you see here in gray, here, these are mainly granites. And this is where the majority of the people are living and trying to make a living from very, very poor soils. I worked in this area for 6-7 years, and it's a hard job to bring soil fertility to an infertile area with infertile soils growing on relatively infertile granites. The second aspect of agrogeology is the beneficial application of rocks and minerals to enhance soil fertility, rocks for crops. And here we go, the 3 steps from exploration to processing and then finally to application of ground rock material to soils. So the first aspects of agrogeology, again, the influence of parent material is illustrated here. In Zimbabwe, this area here is a poor sandy soils, so a low nutrients status soil, low water holding capacity, a sandy soil. It's hard to eke a living out of these soils. And under the same climate, just a few kilometers away, you can see here this picture here with the sunflowers towering over my colleague. This is the same climate, but a different underlying soil. In this case, this was a carbonatite actually. But the basaltic rocks were similar in soil properties. So while we have in the granitic rocks, we have low nutrient status, we have high calcium, magnesium, phosphorus, and trace element status in these soils over the carbonatite or over mafic rock types. High water holding capacities and usually loams. Whoops, what did I do now? Huh? Whoops. Okay. No, I want to go away here. Okay. Yeah. Another area where I work for many, many years is in eastern Uganda. Edna mentioned I did my PhD work in 1971, so more than 40 years ago in Uganda, but I'm going there every year again, and particularly to this igneous complex here, the Bukusu complex in eastern Uganda. The size, from here to here is approximately 15 kilometers. This is a satellite image, and you can easily see from this false color composite that the central part here, which is composed of K-rich volcanics, the carrying capacity of these soils is very, very high, and bananas are just going bananas here. While outside, in the granite area here, you can see this corn or maize plant is not really surviving. So you can see the difference in parent material very well illustrated here. So working in Uganda is great fun because in recent years they got through the World Bank, they got lots of money, and the whole country has been flown, or most of the country has been flown by geophysical companies. I think it was Fugro, yeah, or somebody. And we are using these data now to look at the total count, geology here. You can see here beautiful some granites sticking out, the Mubende granite, another granite here. And you can see here structures. And when you enhance these things and combine the K channel with the geology, you can find beautiful structures and identification of rock types very, very easily. The Finns have been working in this area, and here is just an illustration of some granite areas, here beautifully exemplified, here with the uranium-potassium ratio or uranium-thorium ratio. And here on the sides you can see these dolerite dike swarms. For us, of course, this is interesting that you can identify these lithologies, but we also want to find out what does it mean to soil fertility? What can farmers get out of this? So some other pictures here from a neighboring country, beautiful structures here, a synform illustrated here in the ternary plot up here, or in the total count plot here. These are quartzites, down here some quartzites too. We can easily identify them with airborne geophysics. So the important part now is to relate these two things. So I always go out to any country where I'm going. First I go out with the soil scientists and tell them what are the soils that are the best in your opinion. And this dialogue is already extremely exciting, because they will show you that, oh yes, these are our fertile soils, and you as a geologist can identify and say, wow, yes, these are amphibolites underneath, or dolorite dikes, or volcanics, or if you're lucky, you'll find an anorthosite that we just discovered a few years back in Brazil. You also note that the soil fertility is very variable over gneisses. It depends on the composition of the gneisses, and particularly the composition with regards to mafic minerals. So usually the more mafic minerals, hornblands, biotite we have in these rock types, the higher is the soil fertility. And then of course we come to areas with low soil fertilities over quartzite, sandstones. And here I want to show you something very interesting what we discovered last year in Brazil. Okay, so we do things together. We do things together with soil scientists, with geologists, and we are using these days not only what I was used to, the hammer, the compass, and the hand lens. We are now using fascinating portable tools. So we are constantly using magnetic susceptibility meters, we are using gamma ray spectrometers, and lately we are using also portable XRFs. So we can analyze the rock composition in situ, and we can analyze the magnetic and radiometric properties in situ. So I want to illustrate here a little bit of some surprise findings in northeastern Brazil. Usually I thought that granites have a low soil fertility. So the soils developed from granites are poor, sandy, low water holding capacities, and not much in there. But I have learned to differentiate granites and granites. And we came across this old Australian literature, which is, I think, still in differentiating I-type granites from S-type granites. So here on this picture here, you can see the I-type granites, coarse porphyritic granites containing hornblands and biotite. And on the other side here, you find some leucocratic muscovite-bearing granites, and they have completely different fertilities, but also geophysical signatures. The I-type granites contain quartz, plagioclase, biotite, hornblende, and also magnetite. While the S-type granites, quartz, lots of quartz, leucocratic usually, K-feldspar, plagioclase, and muscovite. And muscovite is something which contains 10–12% K, but never weathers. Like quartz, it's remaining on the soil, and it does not contribute anything to soil fertility. So the soil fertility over these S-type granites is completely different from the I-type granites. So soil fertility very low. You have low P, medium K, not available K, aluminum toxicities, while on I-type granites we have medium soil fertility, elevated calcium, magnesium, even phosphorus and potassium and trace element zinc compositions. So knowing this, we went into the airborne geophysics and said, can we identify these soils, these different soils over different granites geophysically? And yes, we can. Here I show you the geophysical signals of an I-type granite. They have high magnetic susceptibility and low to medium total count, and the K content is highest, much higher than the thorium content. Magnetic susceptibility is high, and when we make ratios of thorium over potassium, we find low, so a negative signal here. And this contrasts strongly to S-type granites. Here we are mapping right now an area with S-type granites. I just show you here the areas with thorium to potassium ratio. Here this is the ternary plot. This area here is the S-type granite, and in these S-type granites really only cowpeas can survive. No corn. Farmers will try, they will fail. It's an infertile granite. In contrast, the I-type granites can support corn. So for farmers, this makes a huge difference. And when we went out with the soil scientists and we showed them this data, they said, wow, look at our map, it's poor. With your maps, with the additional tool of geophysics, we can make wonderful soil maps, new soil maps based on this additional remote sensing tool of geophysics. So yeah, we went into an anorthosite area, which the soil scientists showed us, and it is very low in total count, very low in magnetics, and we can easily map out the area with this particular rock type. And we realized also we can give advice to the farmers, because anorthosites do not contain any potassium, any biotite. So this is an area which has a relatively good fertility but lacks potassium. So we can give advice on the basis of geophysics and soil surveys on management techniques. So the challenges we have is mainly that we can do this in areas where precipitation rate is not too high. In areas where we have more than 2,000 millimeters of precipitation per year, the geochemical and geological signature is largely wiped out by leaching, and we have infertile soils. In areas with, let me say, 500 to 2,000 millimeter per year precipitation rates, the tool of geophysics is just wonderful, an additional tool to map soils and soil fertilities. So there's another limitation, of course. When you use airborne data, you measure total K, and total K does not necessarily mean available K to the plants. So you have to do ground surveys too. So as I mentioned, we go out first with the soil scientists. These guys and the geologists, we provide the framework, and then we do joint interpretations between soil scientists, geologists, and geophysicists to refine soil fertility information, use them for mapping. Now I come to the second aspect of agrogeology. So many areas in the world, particularly in the tropics, have low fertilities, and the usual culprits of low fertilities is usually nitrogen and phosphorus, but in some areas potassium too. So these contain nitrogen. Of course, we cannot provide with rocks. Nitrogen we can fix from the air with plants, or we can go the chemical route with the Haber-Bosch process. But basically, with nitrogen we can't do very much. But with P, phosphorus, and potassium, we have a tool and some resources that we can access and must access for development of many of these areas. Yeah. Okay. Coming to phosphate rocks. There are three types of phosphate rocks. There are sedimentary phosphate rocks, so layered, large-scale deposits like in Morocco or in Florida, North Carolina, and so on. Then we have, and they are usually associated with slightly elevated uranium values. So we have a potential tool there. Then we are looking at igneous phosphates. They are mainly associated with carbonatites. And then we have a relatively new type as biogenic phosphates, bone deposits. So with sedimentary phosphates, we have elevated uranium concentrations. The challenge is usually overburden. If these things are horizontal, flat, to pick them out radiometrically can be a challenge. Igneous phosphates usually have elevated uranium, or more importantly, actually, thorium with the mineral of monazite. And they almost all contain magnetite. So we have some beautiful tools of magnetics and radiometrics. And biogenic phosphates, they have usually elevated uranium concentrations. I give you a tiny little overview here on the phosphate rock resources in Africa. Here on the west side and the northern side, we have mainly sedimentary phosphates. And on the eastern side here, central and eastern side of Africa, we have igneous phosphates. Most of these phosphates, however, are unreactive. And we have to use all kinds of tricks to make them more plant available. And I have been working with graduate students over 20 years on methods of getting them more plant available. So my challenge is the mouse here. Where are you? Ah, here. Here. Whoops. Doesn't want to go. Here. So I have worked most of my professional life on carbonatite complexes in Eastern and Southern Africa, but also lately on sedimentary phosphates, for instance the one in Mali, when it was still accessible, Tilemsi. And you can see here from this map that most of these carbonatite complexes are associated with rifts, with deep seated fault systems, and so most of them, like here in the Western Rift, they are associated here at the edges, or sometimes even inside of the Western Rift, and more higher concentrations of carbonatites are usually where structural interferences are, where one rift meets the other. This is some igneous phosphates associated with ring complexes in eastern Uganda. You can see here nicely 1, 2, 3, 4, like pearls on a string, associated with some deep fault zones. The same thing here. We worked for 5, 6 years on this cluster down here in where the a branch of the western rift was cut by another rift system, and it's at these areas of structural weaknesses where carbonatites usually come out. So exploration for agrominerals includes geological mapping, geochemical, stream sediment samples, but also geophysical, and I did some geobotanical botanical work, geobotanical work on this particular carbonatite, which is probably to some interest to some Australian companies right now because they contain a lot of rare earth. This is the Ngwala complex in Tanzania. As you can see here, these are very old pictures where we were still painting the anomalies by hand and we didn't have things so nicely done as it is today. But you can see easily here when we were looking for igneous phosphate resources that the magnetic anomalies and the radiometric anomalies coincide. Wherever you have a coincidence of a magnetic anomaly because of the magnetite in the carbonatites and the radiometric anomalies, usually thorium anomalies associated with monazite. Here's a neighboring country. You can see that in this area here, in some of these anomalies, they stick out like a thumb from very, very far. Already you can see that there is a carbonatite. Looking in details at this particular carbonatites, you can see high total count anomalies. Where's my mouse? Here. High uranium anomalies, high thorium anomalies, all at the same spot, high potassium, and the potassium is associated mainly with the phenite zone, so the aureole around the carbonatite. Look at the ternary plot here. It's a beautiful anomaly. The magnetic intensity map is showing not such a very clear case, but when you overlay these two anomalies here, the ternary and the total magnetic intensity maps, you can bet this is a carbonatite. We also did some work on smaller anomalies, where we found a radiometric and magnetic anomaly showing anomalous figures. And when we went there with ground truthing, we found these were false anomalies. There was a dolorite dike cutting through a gneiss which was highly enriched in thorium. So one has to have ground truthing. Not all can be done from the air. And here I want to show you the difficulties in using airborne data only. A big complex like here, the Isango-Ikola carbonatite complex, or most of these round complexes, they are relatively easy to pick out. But this one here, the Songwe scarp carbonatite here, a long band 5-10 meters thick only, you could not pick up from airborne geophysics. We had to go and do ground geophysics. Here we went with the gamma ray spectrometer, and we could easily pick out the higher radioactivity, which was clearly related to apatite concentrations, to phosphate concentrations. So we did lots of work here correlating the total count data with phosphate data, and we found actually that usually the phosphate concentration was not in the carbonatite, but just at the edges of the carbonatite, in the phenite zone. So here is this carbonatite. You know, every geologist has a love story to one particular rock type and one particular area. This is my love story. Nguala, where we did lots of geological, geochemical, geophysical work, and we found some high concentrations of phosphates. And I understand now there's an Australian mining company who is interested in the development of the rare earth in this particular area. Radiometric surveys also led to a major biogenic phosphate discovery in northern Tanzania. It's the Minjingu phosphate, oops, where are you? Yeah. Down here, which was discovered, I think, with an old hunting survey when they wanted to find uranium. And they were disappointed when they went to the field, and yes, the uranium concentrations was elevated, but it turned out to be phosphates. Biogenic phosphates, a bone deposit of here bird and fish bones. And this deposit here is an old island in the Rift Valley, which was submerged at the time, and birds were nesting on this island and were defecating and dying. And so this is, it has only 10 million tons of phosphate, but it provides today approximately 2/3 of the phosphate resources for Tanzania. And it is being exported to neighboring countries too. And it was found by geophysics. So I mentioned to you that I work in Uganda for many years, and again we were looking for phosphates. Everybody was pushing for looking for phosphates, focus very clearly phosphate rocks. But the staple food in Uganda is banana. And banana hardly use any phosphorus. So bananas require potassium. So we have to be, in our approach, we have to be a bit more crop specific in our agrogeological exploration. And here the search for K resources in Uganda has kicked in. Actually, it started when I gave a talk at one of those conferences in Entebbe, and they said, oh, we can pick out potassium easily with geophysics. And so we did a survey, worked together with the geologists and the geophysicists, and we picked out a few areas here, mainly granite areas and volcanic areas with high potassium concentrations. My colleague Kato and some other guys from the Geological Survey of Uganda have gone further. They are looking now at all the hydrothermal alteration zones, because they thought that this is the area in ground surveys that they found the highest concentrations of banana plantations. So there is a relationship, and again, geophysics can play a major role in there. We are targeting now potassium in Uganda, and we are looking in particular to silica-undersaturated K-rich volcanics. Here you can see bananas growing directly on some lucite-bearing volcanics, and they are growing extremely well. But we are also now looking a little bit, so this is this area here with phoidites, phonolites, and so on, K concentrations 6–8%, K2O. Yes, it is not like potash deposits in Saskatchewan, but for the local economy, this is, and the local agricultural development, this is very, very rich. So my colleagues have now compiled data on K resources, and you can see here mainly volcanic ashes, but also hydrothermal alteration zones are being looked at as potential zones for potassium for bananas. So, coming to an end, I would like to summarize and say that airborne and ground geophysical surveys are novel additional tools for rapid soil mapping. We have to involve our colleagues from soils, geology, and geophysics. Airborne geophysics is a powerful tool in identifying certain exploration targets for agrogeological resource discoveries. I gave the example of phosphate rocks in particular. But in general, geophysical methods in combination with these other disciplines are novel tools and powerful tools and have a high potential, in particular in these areas which I mentioned before. And maybe the term agrogeophysics is something of a new interdisciplinary science. Thank you very much.
Okay, thank you very much, Peter. Get the microphone if anyone has questions.
I'll read the questions online
Okay.
for you. They can hear me. I'm close. Are you planning to come back to Brazil for a future project on agrogeology, especially in the south region of Brazil?
I can answer this straight. I work with CPRM and Embrapa in Porto Alegre and Pelotas in Rio Grande do Sul. We have the first agrogeological project where these major government agencies have signed an agreement to work together, and every year we have joint field trips and wonderful time in southern Brazil.
There's another question from the Geological Survey of Brazil, of northern Brazil. They love to hear you talk. He says, the name of the person is Firmino Correira.
I know him.
So he says, we have found phosphatic shales in levels, but are not associated regions with high levels of uranium. It's only 7 to 15 ppm. In this case, the mineralization of sedimentary type is associated with facies more calcareous and less reducing conditions. That's a long topic. We know that in some cases worldwide, the mineralization is associated with reducing conditions of rich in uranium. The question is, in the environmental conditions described above, do you recommend the use of some other geological methods beyond radiometric methods?
I think in this area, it's in the Amazon area, I guess. These are sedimentary phosphates. The concentrations of 10, 15 ppm of uranium is very, very low, and this should be no problem at all. I have been working with uranium let me give you examples of uranium concentrations in North Carolina, something like 50 ppm, in Morocco 40 to 50 ppm too. So this is not a big issue.
One more question. How do you measure the available K?
So soil testing method, and it's an extraction technique whereby you are using your soil sample and subject it to some chemical extractions, the ammonium acetate in particular, and then you measure the potassium that is leached out.
Okay, I think the microphone is working. People online can confirm that. So, yes, questions from the audience?
I'm assuming that most of the soils that you'd be looking at in the studies are locally derived from the bedrock, whereas that's often not the case. For example, in Canada, transported. How might agrogeological approaches have to be modified for working areas of transported soils?
It's much more difficult, obviously. The agrogeological work is mainly concentrated in tropical areas where there is no movement or very little movement of soils over the different parent materials. If you're coming to an area where you have glacial movement, it's very difficult. Yeah. But some of them, when you look at the carbonatites here in northern Ontario, they have easily been picked up by geophysics too, despite the fact that there is some overburden on it. Yeah.
Very interesting presentation. How far away are we after the World Bank finances Airborne, radiometrics and magnetics to get a soil fertility map? How much research is still required?
We are very much at the beginning. We tested these S-type, I-type granites in Pernambuco State last year only, and went out with soil scientists to see of how we can refine soil mapping using this additional tool. It can be done relatively fast, but it requires collaboration in the first place with soil scientists. We have to know what we are doing. The problem is that usually one discipline is working along the lines of their specialization and the others on their specialization, and joint work is difficult. First of all, we speak different languages. Soilese versus geologies or geophysics. And to come to a joint understanding of what these signatures mean, that requires some work, but then it can be done relatively fast. So every country is different, obviously, and it has been tested so far only in 2, in Brazil, and we are starting in Uganda now.
More questions in the room?
You mentioned your book, Rocks for Crops. Does that cover much of this in terms of geophysical content and soil science as well? And is that book available? Can you find that?
Yeah, unfortunately, my love for geophysics is old, but I have not included very much in the presentations in these books. One of them is called Rocks for Crops, Agrominerals of Sub-Saharan Africa, and it's online. Yeah, and there I give some case studies, but not much, unfortunately, not much geophysics in it as yet. The second book is you can buy on demand, actually. It's quite interesting. It's book on demand from Cambridge here in Ontario, and it can be bought for, I don't know, 50, 60 bucks. And I'm working on another one right now to incorporate more of our new findings. You must know that this is relatively new, and you gain experience over the years, and then only in later years you incorporate those findings. But I'm very keen of incorporating geophysics into the next book. We have, well, maybe I can say, we are, oops. We are planning, or we are writing right now, a book on the agrogeology of Pernambuco with colleagues from Embrapa, so the agricultural side, and CPRM in Recife. The book is Agrogeology of Pernambuco and should be out next year. And it will be bilingual, like we Canadians like to do, one side Francophone and on the other side Anglophone, and we will do it Portuguese and English, and also turned around halfway.
Another question online. Okay. And this is from Serbia. The main crop there seems to be wheat, and the question is, what type of concentration of K would be good for?
Well, it depends on, K is measured by the soil scientists in centimole per kilogram with an ammonium acetate extraction, and I think it's 0.15 centimole per kilogram. But this is different from what we are measuring geophysically. Geophysically, we are measuring total K, and this relationship has not been established at all between the geophysical signature and the available K concentration in soils. This needs to be done.
More questions?
Yes, thanks for sharing with us some interesting new directions for geophysics. I was wondering two things. One, have you approached or been approached by any of the parties involved with the Geoscientists Without Borders, given the direct benefits to local populations of your work and your investigations? So that's the first question.
Yes, my terms in Brazil are being paid by the Brazilian government with this program Ciência Sans Frontières, so Science Without Borders. But other than that, we had a project supported by all kinds of agencies, mainly here in Canada from the IDRC, International Development Research Center, but I worked for different agencies mainly in East Africa. So it's popular among agronomists. They find this, it's a new approach. Maybe we can contribute something to food security. It's not so much of finding a huge, big deposit, but small deposits for local populations. And sometimes a tiny little liming deposit will do.
No, I understand. I worked years ago in southwest Tanzania. So,
Oh. In southwest, where?
a town called Songea.
Songea, yes. Yeah.
But the other thing is, to what extent did you integrate or seek to integrate multispectral remote sensing imaging in terms of characterizing, soils and soil character?
Yes, we have started with this again in Pernambuco, where we work with the remote sensing guys, and we can make various overlays between their multispectral data and the geophysical data. But again, it's very much at the beginning.
Thank you.
One more question online from Santiago Perdomo. He says, have you tried other geophysical methods? I have read about some work done with electrical conductivity.
No, we have not done it. We have really used only this very basic radiometric and magnetic data so far, and we have not done electromagnetics.
Do you intend to?
It's a matter of having funds to do this, yeah. And it has to be relevant. One has to see when this method has a potential of bringing us further knowledge.
Any more questions?
One more question. Do you see any correlation between available K and lithology or alteration? Any controls like that, or is it completely different set of risks?
It is very difficult. It's very difficult to get proper soils data and relate them to the geology. Soils people do a different way of analyzing their soils than we do. Yeah. So again, the interaction with our colleagues of soils is very important. And yeah, we make some progress in Uganda, but it's a safari, it's a journey. Yeah.
Another one online. It's from Carlos Andrade de Carli. He says, on soybean crops, the farmers used to do a lot of samples, soil sample testing, and he wants to know if those expenses can be reduced by doing some geophysical methods.
Well, that's a bit difficult to answer generally. Soybeans require calcium and they require phosphorus, both of which you cannot easily detect by geophysical methods. But we can help these soybean farmers, certainly, by detecting areas with liming materials and with phosphate deposits.
Okay, so I think that's a wrap. So thank you very much, Peter. It was a very different and very interesting talk. Thank you very much.
So is agrogeophysics something of interest?
The next new thing. Thank you.